Hey Matt, you ready to start this problem? Can you read this one out loud?
A 75-meter-long train begins uniform acceleration from rest. The front of the train has a speed of 18 meters per second when it passes a railway worker who is standing 180 meters from where the front of the train started. What will be the speed of the last car as it passes the worker?
Nice. So for this problem, it seems like we have two scenarios. Matt, what is the velocity of the train in the first scenario when it's 180 meters from the worker?
It starts from rest, so I believe it would be 0.
Nice. What is the velocity right whenever the front of the train gets to the worker?
18 meters per second.
Nice, perfect. So that's scenario number one. Scenario number two is what we're actually going to be solving for. So, what is the initial velocity of scenario two?
Scenario 2, I believe, would be 18 meters per second.
Perfect. Yeah. And then, whenever it actually gets past the worker, the back of the train is located where the worker is. That's the velocity we're searching for, right?
Yes, because it's not when the front of the train reaches the person, when the back of the train reaches the person.
Right. In scenario number one, what is the distance covered?
The distance covered is 180 meters.
Perfect. So that's going to be delta x, 180 meters. In scenario two, what is delta x going to be?
Is 75 meters a factor of that?
Yes, perfect. So I drew out our two scenarios. We have scenario one, the initial velocity 0 meters per second. Its final velocity is 18 meters per second. Scenario two, this is what we're actually solving for, is the final velocity in scenario two, whenever the back of the train is passing the worker. We have our scenarios. I'm going to start writing out the three kinematic equations. Number one, we have v final equals v initial plus acceleration times time. Two, we have, that's a mistake. Number two is delta x equals the initial velocity times time plus 1/2 acceleration times time squared. And the third one is the final velocity squared equals the initial velocity squared plus 2 times acceleration times the change in position. We're actually going to be working backwards on this problem. Let's talk about scenario two in isolation first. In scenario two, what are we looking for?
In scenario 2, we have to figure out when the last car reaches the railway worker.
Are we looking for when? That would be a time. Specifically, what do they want?
Or do they want the final velocity of that?
Yeah, exactly.
Okay.
So we're finding the final velocity. That immediately eliminates our second equation because it doesn't include the final velocity. So we're left between the first and the third equation. Let's try and figure out the information we're given. We have the initial velocity, we have the distance. We're missing acceleration and time. The first one includes acceleration and time. The second one just includes the acceleration. So I'm going to pick the third equation here because it has the least unknowns. Just acceleration is what we're looking for. We don't have that acceleration, but we know that if we had it, we could solve for the final velocity. So before I plug anything in, we're going to go to the first scenario and see if we can find the acceleration in that scenario. Do you understand why we're doing that?
Is it because we can't solve the final problem without solving for one of the variables that are still unknown to us?
Yeah, exactly. We're kind of searching for the unknown variable, which in this case is just acceleration. So in scenario one, if we are new unknown, we have to find the acceleration. Now for this one, we're given v initial, v final, and delta x. Which of our three equations includes v initial, v final, and delta x? And A. Does the first one have those four variables?
We don't have distance in there.
Right. And we do have time, which adds another unknown. So we wouldn't be able to solve for the acceleration. So it's not the first one. How about the second one?
So the second one, while we have the distance, we don't have v final.
Right. And it also has the time. So it's not the second one.
Yeah.
Does the third equation work?
Even without knowing the v final, I think it's possible to figure out the acceleration by completing problem 3.
So for the first scenario, we actually know v final.
Oh, okay.
This is tricky. The first scenario, v initial is 0 and v final is 18 meters per second. Let's use the third equation and fill it in with our first scenario. What is v final equal to in the first scenario?
18 meters per second.
Right, so we have 18 squared. What is the initial velocity equal to?
The initial velocity equals 0 because it started from rest in that scenario.
Perfect. Do we know the acceleration?
We do not know the acceleration yet.
Right, that's what we're solving for. And what is the change in position in the first scenario?
The change in position, is that 180 meters?
Yeah, perfect. Okay, let's do a little bit of algebra to solve for the acceleration, which we can then use to plug into the second scenario. Nice. So what I'm doing is 18 squared equals 2a times 180. Now, I'm just going to swap sides. I have a over here, and I divide both sides by 2 and by 180 to isolate a. So I end up with a equals 18 squared over 2 times 180. Now, when you put this into your calculator, it's important to use parentheses in the denominator to make sure that you're dividing the top by both of these and not dividing it by 2 and then multiplying it by 180. Let's take a second and calculate the acceleration. 18 squared divided by open parentheses 2 times 180 close parentheses. Hit enter, and my answer, I get either 9/10 or 0.9 meters per second squared.
All right, I was able to get that too.
Perfect. I'm going to put a circle around that. This was our calculation for scenario number 1. Let's use the calculation for scenario number 2. And we already decided which equation we're going to use for scenario number 2, right?
Right.
Which one was it?
So we're going to use number 3.
Perfect. Okay, what is our final velocity in scenario number 2?
For scenario 2, is that what we're solving for?
Yes, that's kind of a trick question.
Okay.
So we just
don't know
write
that
it down as is. Exactly. What is our initial velocity in scenario 2?
Would that be 0.9?
No, that's the acceleration.
Oh, we have the, okay, so we can plug that in later.
Mm-hmm.
But for scenario 2, is that 180?
Yes. Well, it's 18. 18.
18, okay.
Sorry, I got thrown off. So the initial velocity is 18. Maybe you had trouble seeing it. That's okay. 18. Oh, I wrote 180 because I got a little confused. 18 squared. And then plus 2. The acceleration is 0.9, right?
Oh, that's the acceleration that we just solved for. So
Exactly.
That's where it gets plugged into.
And then what is our change in position, delta x?
Delta x, this time, is it 75?
Yeah, perfect.
Okay.
Now, this problem doesn't take very much algebra at all. All we have to do is take the square root of both sides to get rid of that squared above the v final squared. And we end up with v final equals the square root of 18 squared plus 2 times 0.9 times 75. Be careful calculating this. Make sure that everything falls under the umbrella of that square root symbol. On a calculator, you do this with parentheses. So I'm typing in the square root, open parentheses, 18 squared plus 2 times 0.9 times 75, close parentheses. Let me know what you get for your answer, Matt.
I got 21.42.
That's what I got. And it's, what are the units?
The units for this, would they be meters per second?
Yeah, perfect, because it's a velocity. Nice. That's our final answer. That's how fast the train will be going whenever the rear of it passes the person standing there.
And this problem had 2 steps because in less complicated problem. It would just be when the front of the train reaches the person, but we had to know
Yeah.
how long the train was to know when the back of the train reached the person, and that's why
Yeah.
it was a two scenario problem.
Yeah, exactly. We had to work our way backwards in order to get the missing piece, which was the acceleration. Good stuff.